We're going to talk a little bit about the ballistic pendulum. You can see it in this video if you can play it. Not sure if you can, but if you can, that will work great. Otherwise, there'll be a link to it that you can check out as well. The basic setup of it is we've got an object that is launched forward. You can see the little arrow in the picture. Okay. It embeds itself into a block on a string, like a regular simple pendulum type thing. And the block goes upward because of the momentum that it gets or the movement from there, and it swings up until it reaches a certain height. The velocity is 0. That's why it's a ballistic pendulum. The little thing embeds itself in and it swings upward. What gets conserved? Well, momentum does, because the little stick or arrow or bullet or whatever it is has momentum, and it conserves that momentum because there's no external forces. There's only internal forces between them during the collision. Okay. But as it swings upward, it's going to conserve energy. You can see it's going to swing upward, and it's going to conserve energy there too. And you can see what kinds it has too. When it's at the bottom, it's moving a lot. It's going to have kinetic energy, energy of motion. And as it swings up, it's going to trade that kinetic energy for gravitational potential energy. Okay. We're going to work the equations. We're going to call the mass of the arrow that sticks in m1, and we're going to call the velocity of the arrow v1. We're going to say that the block has a mass of m2. It has no velocity initially, and then it's going to have a velocity of 0 when it gets to that maximum height above its initial station. So first, we're going to start with the momentum of the arrow m1v1, and we're going to conserve it. We're going to set equal to the momentum of the block after they collide, which will be m1 plus m2 times v. The kinetic energy at the bottom is going to equal the gravitational potential energy at the very top where the velocity is 0. So it's going to be 1/2 mv squared equals mgh. That's going to be 1/2. M is going to be the total mass, m1 plus m2, times the velocity, which is going to be that giant expression, m1 v1 over m1 plus m2 quantity, all that squared. Okay. And it's going to equal m1 plus m2 times gh. One of those m1 plus m2 is going to divide away, and we factor it back out. H is going to end up being equal to m1 squared v1 squared over 2g times m1 plus m2 squared. If you work out the units of all that, it does work out to be just h. Okay, there's the equation from before. It actually appeared. Okay. But wait, some of the problems won't tell you what as for the height is. They'll ask what L and theta are. Okay. And those are kind of tricky things. Okay. So L is going to be the length of the whole thing, and theta is going to be the angle that it makes with the vertical as it goes up. Okay. And you can see that that's pretty doable, it turns out. Okay. And I'm drawing in the triangle so you can see. Okay. That, like, when we calculate that out to find the height, we're just going to take the length of the whole string and we're going to subtract off the section of the string. That's going to be a height when we get there, or when it gets to the maximum height. Okay. So you can see we're going to call that L cosine theta. So I'm talking about like this section here. That's going to be L cosine theta. And then we're going to take the whole length, because that's going to be the bottom length. That's going to be the bottom L. And we're going to subtract those two from each other. Okay. And when we do that, so the height, this section over here, is just going to be the difference between those. The L minus L cosine theta. This is another way to work that exact same problem. It's really not anything that's a super big deal. All you have to do is subtract those two and you can get that same height you had before. And that's how you work the ballistic pendulum problems.